So this will be a little review of some definitions, and we'll start by playing a game. It's not a very fun game maybe, but we'll call the game standard position, not standard position. So the way that the game works is I draw an angle, and we have to decide if this angle is in standard position and put it on this side with the yes, or not in standard position and put it on this side, no. There we go. So here is our first angle. It goes like that. Is that angle in standard position or not in standard position? Yes. So we put it on this side, on the yes side. Then we draw another angle. I don't need arrows there, but I'll go, we'll go here. Is that angle in standard position or not in standard position? So this one is a no. How about that one? This one is, okay. Another one. That one is a no. That one is a no. Got a little scary there. How about that one? That one's a yes. Question.
So the angle doesn't, like the arrow doesn't have to go counterclockwise for it to be.
The arrow, apparently this one doesn't go counterclockwise, right? This one goes clockwise, and it is in standard position. So this is the standard. This is what we're looking for. What makes something standard position? And the reason I make this yes-no game is to start to figure out stuff like that. Right? We can, sometimes when we just write a definition down, you don't notice some intricacies. And this was the first one that kind of rubbed you the wrong way when I put it into the yes category, right? That it can go in the opposite direction. That one's a no. Ooh. Whew. Whoa. What? Those 8 examples, how do we feel? Do we feel like we can make the definition of standard position clear? Or do you still want to, are there still some examples that make you feel like, I don't think I've seen everything? So, do we need some more examples, or do we want to start making this definition? You want to start making the definition? All right, so for standard position, what has to happen for an angle to be in standard position? What do all the ones in the yes side have that the no side doesn't?
I don't know how to word it properly, but the arrow indicating the angle always originates from the positive x-axis.
Okay, so the place where the angle starts always starts from the positive x-axis. We can't just say x-axis because we have one over here that starts at the negative x-axis, right? So for an angle to be in standard position, it must start from the positive x-axis. And that's the key thing for an angle in standard position. And then these ones here are all positive angles. And as soon as you go in the opposite direction, this one here would be a negative angle. So why do we have standard position? Well, it's important for communication purposes. If you want to tell someone, I want you to think about an angle of 45 degrees, well, then you'd be thinking of an angle in quadrant 1 in standard position would be in the coordinate system like this first one. And if you wanted to think about an angle of 100 degrees, you might look at this second one, just past 90. And so it gives everybody who's talking about an angle the same visual, the same idea. You'd have to have more descriptions necessary to describe some of these ones. Okay? This one in particular is sometimes used in navigation when they say a bearing. Have you ever heard, did you do bearings in grade 11? No? So they would say this is due north. And if you would go at a bearing of 220 degrees, you start at due north and go around in a clockwise direction. It's a different way of measuring. For what we're going to be doing, we're going to have a lot of our angles in standard position. That's definition number 1 that we're going to review. Definition number 2 is a reference angle. So if I draw an angle of 30 degrees, what's the reference angle? First of all, I'm going to draw angles in standard position, so this angle of 30 degrees would mean that the 30 degrees starts here and goes to there. And so if theta, we use that for angles a lot, the Greek letter theta. If theta is 30 degrees, we write a reference angle with a little r beside the theta. What would the reference angle be? 30 degrees. And if I drew an angle of 150 degrees, so in this case, my reference angle of 30 degrees is right here as well. If I drew an angle of 150 degrees, what is the reference angle? It's 30 degrees. Where would I draw that reference angle? Right here, right? And we could also draw one in quadrant 3. Could you draw an angle in quadrant 3 with the same reference angle? Well, if I went to quadrant 3, this angle would be what? So that my reference angle is 30 degrees. 210. And that reference angle would be right here. And finally, I could also do one in quadrant 4. Which would be 330 degrees, which would be a reference angle of 30 degrees. Some things to be careful with. I find this one really tempting. What is the reference angle for 260 degrees? It'd be 80. But what's really, really tempting is because it's so close to that axis, sometimes you're going to be tempted to say 10 degrees. What would the reference angle be for 270 degrees? 90 degrees. What is the definition of a reference angle? So I'm going to erase this and this for now. Our definition of a reference angle. So based on what we've drawn here, we've drawn a bunch of reference angles. A reference angle it's always positive, so we'll write the positive angle Does anybody know what the line where an angle ends is called? It's called the terminal side of an angle, because that's where the angle ends. So it's the positive angle between the terminal side or terminal arm and what? So we take the terminal arm, so here's where my angle ended, and I'm going to find the angle between it and what? We have to go to the nearest x-axis. So that's the definition of a reference angle. Another thing of review, why are reference angles important? What do they tell us? How are they related to trigonometry? Well, if I were to do sine of 30 degrees, cos of 30 degrees, and tan of 30 degrees, and get values here, so I'll go to my calculator, make sure your calculator's on degrees. Sine of 30, cos of 30. tan of 30 those are the values that you got on your calculator. Last year in grade 11, you memorized these. Do you still remember them? No. All right, you memorized that this was a half. This was root 3 over 2. Okay? And this was root 3 over 3. You need to have those memorized again for this year. You have to remember the exact number, the root 3 over 3, the root 3 over 2.
But we don't have to memorize that root 3 is 0.866.
No, you don't need to remember that. Root 3 divided by 2 is 0.866. Okay, but I will expect you to know that 1/2 is 0.5. You want to memorize 0.866 instead of 1/2? I don't know. I know. No, you have to memorize root 3 over 2. Exact values. The problem with these ones is the second ones are actually approximations. So I should have the approximation signs there because I've rounded instead of written an exact value.
But if we memorize just like 3 over 2, we don't need to know like that.
If you write root 3 over 2, that's an exact value. You should have the equal sign. But that's just a little other review. The main thing we were looking at here is what happens and why do we learn reference angles? Well, we learn reference angles because if I go to these angles in quadrant 2, if I do sine of 150, cos of 150, and tan of 150 on my calculator, something interesting happens. Sine of 150 also is 0.5. Cos of 150 also is 0.866, but now there's a negative sign in front. And tan of 150 is negative 0.577. So you're like, that's interesting. Those numbers are the same. And when we go to 210 and 330, it's the same thing. So when I do sine of 210, it's also a half, but this time it's negative. Cos of 210 is also 0.866, but this one is negative. But tan of 210 is equal to positive 0.577. And same thing happens with 330 degrees. Sine of 330 degrees is 0.5, but it's negative. Cos of 380 degrees is 0.866, but it's positive. And tan of 330 degrees is negative 0.577.
How do you handle the negatives?
Oh, the cast rule. So if I go through this and put a purple box around the ones that are positive, all the ones in quadrant 1 ended up being positive. In quadrant 2, it was only sine. In quadrant 3, it was only tan. And in quadrant 4, it was only cos. So what rule was this? The cast. Nobody learned it as the Astica rule? No? You learned it as the cast rule? So that shows up there as well. Where things are positive and where they're negative. And the reference angle is important because if you know what sine of 30 degrees, then you know what all of the other angles are with the same reference angle. The idea behind it is because of triangles, right? Sine, cos, and tan are triangle-based. And so if I were to draw a triangle right here with 30 degrees, the opposite side would be 1, the hypotenuse could be 2, or any multiple of that, but the ratio between the opposite side and the hypotenuse has to be a half, because that's what sine of 30 tells me. Sine of 30 is a half. That means the opposite side divided by the hypotenuse has to be a half. It could be 4 and 8, doesn't matter. But when I go to the angle in quadrant 2, and I want to draw a right angle triangle, where does my right angle triangle appear? Over here. It's the same triangle. Bigger or smaller, of course, could be. But there's still a 30 degree here, which makes the same triangle, which means that this side to this side, the ratio has to stay a half. I mean, it might be 1 and 2 again. Maybe I drew this one a little bit bigger. It's 1.5 and 3. But it doesn't matter how big or how small, that ratio stays the same. And sure enough, you could draw triangles in quadrant 3 and quadrant 4, and you have the half as well. We're going to connect these angles to working around the circle, and we're going to also see why the cast rule works out that way. So the definition of a reference angle is just the angle between the terminal arm and the nearest x-axis. But it also is important because once you know a reference angle, then you know all the angles that go with it. And that leads us to our last definition that we're going to look at. And this one might be new. Have you heard of coterminal angles? Or did you talk about coterminal angles in grade 11? I think this is a new definition. It's a really easy definition because the definition itself defines it. I like definitions like that, where you read the definition and you're like, oh, this makes sense by the definition. X-intercept is a good definition because the word itself tells you what they're talking about. If you take French immersion, they make up some crazy word that does not have anything to do with x-intercept. Right? They used to, yeah, it doesn't matter. Okay, coterminal angles. Two angles are coterminal if they share the same terminal arm. In other words, if I take 30 degrees, 30 degrees is coterminal with negative 330 degrees. 30 degrees is also coterminal with (390 degrees. Maybe we should clarify in our definition here two angles in standard position. Two angles in standard position are coterminal if they share the same terminal arm. And this is easy because we've got the word terminal in and co in our definition, right? And in the English language, if you have co in front of something, it means to share, right? Two organisms coexist. They share the same area. We've got cooperate, operating together, sharing, working together.